Welcome to the Southwest Hearts Astronomical Society and tonight's talk about the planet Mercury with Chris Hooker. Before that, we've got a short news item presented by Len Mann.
Well, this is about the perfect solar system, so called by the BBC. At the end of last year, Dr. Raphael Luque of the University of Chicago led research and described this solar system known as HD 110067 as the perfect solar system. It's just 100 light years away in the constellation of Coma Berenices. It was studied by NASA's TESS telescope and the European Space Agency's CHEOPS telescope. And this is a graphic, obviously, representing the star with the 6 planets orbiting. They're similar in size and they rotate in harmony, but more about that later. It was presented as the perfect solar system, but I'm not sure about that definition. We'll talk about that later. So what is an average solar system? So far, we've found 5,500 exoplanets in over 4,000 star systems, and some patterns are emerging. It looks like our solar system is not average. In some ways it is. Firstly, our star is a main sequence star of average brightness. And secondly, half the stars we see around us are younger than our sun and the other half are older. But most planetary systems appear to orbit much closer to their star than ours, even accounting for the difficulty in detecting planets further out. It seems that ours are spread out a lot more than usual. Gas giants like Jupiter are common, as are super-Earths. That's planets bigger than the Earth, but smaller than Neptune, which is about 4 times the diameter of the Earth. They're also referred to as sub-Neptunian planets. They seem to be the most common sized planets in the galaxy, yet we don't have any. Our solar system had a very tumultuous beginning. The disk of dust and stars around the sun formed the planets, but unlike the star in question today, there were a lot of collisions. It's also believed that our gas giants formed much closer in towards the sun and then migrated outwards. This is another artist's impression of the star, with its planets transiting in front of it and causing a dip in the light from the star. That's how we know the planets are there. We know their orbital periods and their size, etc. I was surprised to read that the star is 12 billion years old. It's a bit smaller than our sun. It's about 80% smaller, actually. I thought that our Milky Way, I previously read, was only 10 billion years old, but no, that's old information. They now believe that our galaxy is 13.6 billion years old. I formed just 200 million years after the Big Bang. Our sun won't last 12 billion years, but this star can because of its smaller size. Another difference with our solar system is that this star is in a triple star system, but the others are so far away that they don't really affect this star and the forming of the planets. This is my last slide. So all 6 of the planets are between 2 and 3 times the diameter of the Earth. They all formed neatly in an orderly fashion, as you can see from this drawing. And they're all in synchronism as well. The inner planet will travel around its star 3 times, and the second one will do it twice in that same period. And then the next one is also 3 to 2. The next one is 3 to 2. And then the next 2 are 4 to 3, which is a very bizarre synchronous system. In fact, so when the inner planet goes around 6 times, the outer planet goes around once. They all have atmospheres, apparently, so the James Webb Telescope will be able to probe their constituents. We don't know yet if they have solid surfaces. Another bizarre fact is how close they are to their star. They're all within the orbital distance of Mercury. compared to our solar system. And the innermost planet orbits in just 9 Earth days. They're all not inside the habitable zone, so we don't think they're good candidates for life, but you never know. So is it the perfect solar system? I guess it depends on a point of view. It's certainly unusual, and it's possibly even unique. And that's the news. Thank you.
Okay. Well, good evening. Thank you for inviting me here to give a talk about the planet Mercury. As it says there, I am the Mercury coordinator of the BAA Mercury Venus section. And that role doesn't really come with a job description. As I found out when Paul Abel asked me to do it after he became section director about 5 years ago, I said, okay, what's it involve? And he said, not sure, we'll think of something. So I've largely been making it up as I went along, which is fine. I'm quite happy with that. But obviously one of the things that I have to do is try and encourage people to observe Mercury and report their observations. And that's part of that is coming and giving talks about it. So that's why we're here tonight. Okay, so I'm going to basically go through what we know about Mercury and the various ways in which we discovered that over time, visual observations by eye and then with telescopes and other things from Earth, and finally, more recently, spacecraft visits. And then I'll talk about the kind of observations that we as amateurs can make now that we are able to do that more easily with better equipment. The earliest historical record of Mercury, or the earliest written record that we know about, is on these things called the Mulapin tablets, which are thought to be around 1300 BC, approximately. And they were found in the ruins of ancient city of Nineveh, which is in what is now northern Iraq, in the library belonging to this king, whose name I'm not going to try and pronounce. They're written in cuneiform text, which has been deciphered. And they describe a whole load of astronomical information, in particular things like when stars rise and set, which is obviously important if you're trying to set up a calendar for planting crops and so on. And they also mention positions of stars and movements of planets, including Mercury. So that is probably the oldest written record that we have of Mercury. What you can't get from that picture is the size of this thing. This is actually about the size of a pack of playing cards. So it's really quite small. And that text is incredibly small and fiddly to read. So hats off to the people who actually did that and managed to decipher it. The Mercury has been considered as a messenger by many cultures, probably mainly because of its rapid movement across the sky. Mercury, or Hermes, was the messenger of the gods in classical mythology, and that's a rather nice statue of him there. He's got winged sandals and a winged helmet to help him go fast, and this caduceus, as it's called, the serpent staff, is a symbol of peace, which was probably meant to convey the message, I'm only the messenger, don't shoot me. So, basic facts about Mercury. What do we know about it? Obviously, it's one of the 5 naked eye planets, and it's been known for millennia. Long before those records were written, people were aware of it in the sky. It's the smallest of the true planets, now that we discard Pluto. And it's actually slightly smaller than both Ganymede and Titan by a few percent. But if this was orbiting around Jupiter, it would just be another slightly smaller moon. It actually orbits the sun, of course. Oops, wrong one. Too many. It orbits the sun once every 88 days, and its distance varies quite a lot because its orbit is highly eccentric. It's the most eccentric of all the planetary orbits. And it's also most highly inclined to the ecliptic, about 7 degrees. And that combined with the structure of Mercury may suggest something about its history, which is a bit speculative. We'll come on to that. The difficulty for us for observing it is that it never gets more than 28 degrees away from the sun at its furthest. And so we're always trying to observe it in the twilight or in the morning twilight, evening twilight. But if you actually want to observe it properly, you need to do that during the day. And I'll come on to the issues associated with that when I'll talk about the observations. Other things about it, its surface temperature at perihelion can reach 430 degrees Celsius at the subsolar point. But even that is not as hot as Venus. Venus can get up to nearly 480 Celsius, but that, of course, is because of the greenhouse effect and the thick atmosphere. Mercury is unusually massive for its size, which implies it has a very high density. And that, again, is suggestive of past history of what happened to it. And it does have a magnetic field because we know it's made quite largely of iron, and that's not perhaps a surprise then. In fact, it doesn't rotate in the same period as it goes around the sun. That was thought to be the case for a long time, but it's now been shown that its orbital period is 3 halves of its rotation time. So every 2 orbits, it rotates 3 times on its axis. So it is locked to the sun. It is synchronized to the sun, but it's a 3-to-2 so-called orbital resonance rather than an actual tidal locking. Its axial tilt. Now, this is the discrepancy or the difference between the perpendicular to its orbit and its rotation axis. So in the case of the Earth, our rotation axis is 23 degrees to the plane of the orbit, which is why we have seasons. Mercury's tilt is 0. It's actually 2 arc minutes. It's near 0, it makes no difference. And so there are no seasons on Mercury as there would be on Earth because of the axial tilt. However, the fact that it is 50% closer to the sun or 50% further away from the sun at aphelion probably gives it effective seasons in terms of variation of temperature. So it's visible to us, as I said, during what are called elongations, either eastern or western, depending on which side of the sun it appears, and it's visible during the evenings on eastern elongations and the mornings in western elongations. And in between those, it undergoes conjunctions when it passes either behind the sun as seen from Earth or between us and the sun. And when it's between us and the sun, very occasionally it actually is directly between us and the sun, and we see a transit for a short time, and we see Mercury in silhouette. The last time that happened was on the 11th of November 2019. Anybody see that? Show of hands, who saw that? No? Okay. I can't see you. There's light shining in my eyes. The next transit is not until 2032, again in November. So the visibility of Mercury depends very strongly on its orbital geometry. And this is a diagram looking down from the north of the ecliptic, showing Mercury's orbit inside and the Earth's orbit to scale. The sun is not to scale. The shaded area is the part which is below the plane of the ecliptic, and the open part is north of the ecliptic. So this is the line of nodes here. Perihelion is here, and this is aphelion. And this is the Earth's orbit with the months indicated, and both planets are going around the sun in an anti-clockwise direction. So you can see this is the discrepancy, the difference between perihelion and aphelion distances. This is about 50% larger than the perihelion distance. Now, the combination of that variation of distance and the angle to the ecliptic affects the visibility very strongly. So this is a screenshot from Stellarium for the 30th of April 2022. This is the spring in the northern hemisphere. The ecliptic is at a steep angle to the horizon, and at that time Mercury was north of the ecliptic. So even though this is a screenshot for an hour after sunset, Mercury is still nearly 10 degrees high in the twilight. A good location, a good time to observe it. A similar thing happens on autumn mornings, when again the ecliptic is at a steep angle. Mercury is not quite so far north in this case. This was September 2022. But again, spring evenings, autumn mornings are the times to try and see Mercury if that's what you want to do by eye. And that's true whichever hemisphere you're in, because in the southern hemisphere, the seasons are reversed and the angle of the ecliptic is reversed. And so you actually get the same rule of thumb as to when to see Mercury. The transits occur when Mercury is close to one of its nodes, here or here. A good way to visualize this is if you think of Mercury as being a bead sliding around a wire, which represents its orbit, we will only see a transit of Mercury when we also see the wire silhouetted against the sun from our point of view. And so that only occurs when the plane of Mercury's orbit crosses the plane of the ecliptic, which is here and here. And if Mercury comes to inferior conjunction within about a couple of days of those times, then we will see a transit. Quite clearly, when it's a May transit, this one here, Mercury is further away from the sun, so it appears larger to us. It appears about 12 arc seconds across, but it's moving more slowly because it's further from the sun, and so the chance of it being there is less, and that's why the May transits are roughly half as common as the November ones, where Mercury is close to perihelion and it's moving more quickly in its orbit, but it appears smaller during the transit. And these transits don't last as long as these ones. A good May transit, a central May transit, will be visible from roughly 3/4 of the way around the Earth at some point or other. And that's the picture of the last one, which I took. We were doing an outreach event at a school near Newbury. And luckily we had some clear skies and we were able to show the children Mercury silhouetted against the sun, which was rather nice, and they enjoyed that very much. So Earth-based observations of Mercury, which was the first sort of tranche of observations, if you like, were purely visual initially, just seeing it in the morning sky and then something else, or maybe the same thing in the evening sky, and noting that it never got very far from the sun. Once the telescope was invented, various observers looked at Mercury and tried to see what it looked like. Galileo observed it with one of his primitive telescopes, but it wasn't powerful enough or probably optically good enough to detect the phases of Mercury. He could see the phases of Venus, which of course is a much bigger planet, but he didn't see the phases of Mercury. That was left to another Italian, Giovanni Zuppi, only a few years later, about 30 years later. And obviously that gave further confirmation to the heliocentric model, because Mercury is like Venus. Other astronomers since then have mapped and imaged and drawn Mercury with better and better telescopes. And I've got a few examples to show you here. This is the first one, Schiaparelli. Now, I don't know when he drew this. Those are his dates up there. They're not the date when he drew this map, but as you can see, he saw linear features on Mercury similar to the ones he saw on Mars. I don't know if he called these canals, but that's a very similar looking thing. The worst example of canals on Mercury is Percival Lowell, who saw this concoction in 1896 using the Flagstaff telescope. I find that ridiculous. I mean, Lowell also saw canals on Venus, for goodness sake, which completely destroys his credibility as an observer, in my view. But anyway, that's what he drew. There was a theory that what he was actually looking at was the shadow of the blood vessels in his retina, because he was using a very high magnification. So the exit pupil would be really small and it would act as a little point source which projected the line on his retina like that. That's a speculation, but it's plausible. This is about the first reasonable looking drawing of Mercury by a French artist and amateur astronomer, Lucien Rudeau. And this looks, kind of like a rocky planet might seem if it was really small and you were looking at it from a long way away. It's a plausible looking drawing. And this is the one by Eugene Antoniadi, 1934, a few years later. And these two look, not the same, but there were definite similarities. You can see similar kind of features, not in the same places, but broadly similar. Now, you might notice that all of these maps that I've shown you so far only show a single hemisphere. And that was because everybody believed that Mercury's rotation was synchronous with its orbit, and therefore you could only see one hemisphere of Mercury illuminated. And if that's what you believe, that's what you'll see, generally speaking, because the markings are sufficiently vague and indistinct that you can probably convince yourself that what you're seeing is the same hemisphere all the time. And it wasn't until radar measurements were made with the late lamented Arecibo telescope that showed Mercury's rotation period was 58.6 days. And therefore you could actually see the whole of Mercury at different times. And then we got this map, excuse me, by Dolphus using the 33-inch refractor at Meudon in Paris. And he drew what is now, well, the more or less definitive visual map of Mercury. And this was adopted by the IAU as the map of Mercury. And it's pretty reasonable. It shows albedo features. If you think about it, this is probably sort of 6 or 7 arc seconds up here. So these features are around about half an arc second across, which is kind of what you might expect with a good quality telescope in good seeing and a good observer who was recording what he saw accurately. So that's, sorry, a bit of a cough. So those are the visual observations. Now I want to show you one more very interesting observation, which you've got a preview of briefly. This is a telescopic image of Mercury taken using the Mount Wilson 100-inch reflector in 1998 with a video capture technique, very similar to how we would image a planet today. Except I think this was a videotape type camera, and they recorded the video on tape and then had to do a lot of processing to select the frames and stack them together. They also applied a rather odd contrast stretch because this is the terminator, and they adjusted the brightness to allow for the sun angle. And so it's all as if the sun was directly overhead, which is why it's that slightly strange looking crescent. The interesting thing is this bright spot here. And that is a feature on Mercury called Nathair Facula. I'll come back to that when we get onto the satellite images. Other observations of Mercury that were made by various people included a determination of its mass by looking at the perturbation of short period comets. And that was done by Simon Newcomb. And if you look at how things like Comet Encke get perturbed as they go near Mercury, you need to have a comet that's going into the inner solar system, obviously, and goes fairly close to Mercury. He derived this mass of 3 × 10 to the 23rd kilograms, which is 5.5% of the mass of Earth. And that implies Mercury has a very high average density. In fact, it's quite similar to the density of Earth. The rotation period, as I said, was long thought to be the same as the orbital period at 88 days. And it wasn't until 1965 that radar observations proved that actually it was 2/3 of the orbital period. Now that is consistent with the visual observations given the time between elongations. You actually do see very much the same face of Mercury when it's favorably placed for observation. And so it's understandable that the early observers saw what they thought they saw, partly aided by their belief in the rotation period. This one is, I think, the most interesting one. At least I was researching this talk and I found this out. And this is Mercury's libration, which is not quite like the lunar libration, which is based on an interaction between the orbital speed of the moon and the rotation of the moon. This is caused by gravitational torques due to the fact that Mercury is not a perfect sphere and its very eccentric orbit means that it gets pulled and pushed by the sun in various places. This was measured by a group at the University of Belgium using very sensitive Doppler radar techniques. I don't know the details of that. And they found that Mercury was rocking backwards and forwards by about 35 arc seconds. Now that's not 35 arc seconds of angle in the sky. That's 35 arc seconds of longitude on Mercury, which corresponds to about 400 meters at the equator. That's an incredibly precise measurement to be made at that distance. But what it tells us is that Mercury cannot be completely solid. Because if you work out what that amplitude should be for a completely solid body, you know the mass, you know the size, you know the density, you can work out what the moment of inertia should be and how it should respond to those gravitational pulls. And if you work all that out, the answer you get is about half of this value. And so what that shows is that the bit of Mercury that's rotating must be decoupled from some of the mass, and that implies that there is a liquid shell inside there, so that there's a solid crust, but part of the interior must be molten still. So coming on to spacecraft observations of Mercury, there have been 3 spacecraft so far which have visited Mercury: Mariner 10 in 1974 and 75, Messenger, and Bepi Colombo, which has flown past Mercury a couple of times but has not yet entered orbit. So Mariner 10 was the first, and this was not an orbital probe, it was just making flybys. It was actually the first probe to visit 2 planets, because they started it off and it did a flyby of Venus and sent back some very interesting pictures of that. And that deflected its path in towards the inner solar system, where it flew past Mercury 3 times in February 74, March 74, and September. That was, sorry, March, yeah, those dates there. Unfortunately, the time between those flybys was exactly 2 orbital periods of Mercury, about 176 days. And so the same hemisphere of Mercury was illuminated on all 3 occasions. So we only saw about 45% of the surface. But that's 45% more than we had before, so we can't really complain. So this is a mosaic of images from Mariner 10 on the inbound leg of the first flyby, and it shows a rocky, cratered world that looks quite like the Moon, apart from the fact there are no dark mare regions. This is the outbound image from the same flyby, slightly larger phase, but still much the same. There are some tonal variations, but there's not really much smooth area there. There's a lot of cratering, which is perhaps not surprising, because in the inner solar system, that's where most of the projectiles would come flying in from outside, and you might expect a lot of craters. They did detect an interesting feature, which is this, you can just see it down here, this kind of arc of rings of mountains and things. And this is about 1/3 of the famous Caloris Basin, which is one of the largest impact features in the solar system. It's about 1,500 kilometers across. It's enormous. The multi-ring impact basin. Unfortunately, Mariner didn't see all of it, and it was left until the next probe to actually image it fully. On the exact opposite side from Caloris, Mariner discovered this really rough and broken area, which you can see here. Now, obviously, there have been subsequent impacts which have produced these smooth, flooded areas where rock has been melted. But the rest of it is really shattered and broken. And that's believed to be a consequence of the shock waves from the Caloris impact being focused by Mercury's core and causing massive earthquakes and disturbances on the exact antipode side of that. So the second probe to Mercury was Messenger. And that Messenger is actually an acronym, which I can't remember. It was something about Mercury surface, something or that environment, blah, blah, blah. One of those NASA acronyms that they make up after they've thought of the name. It was launched on 3rd of August 2004 and got to Mercury in March 2011, taking 7 years to get there. And it then spent 4 years collecting data and was finally crashed into Mercury in April 2015. Now, taking 7 years to get to Mercury seems a bit excessive, but actually Mercury is really hard to get to. That's a quick picture of the probe that shows the solar panels, which it did have, although they don't need to be very large at that distance from the sun. The most important feature was probably the heat shield, which protected the rest of the spacecraft from the fierce solar irradiation, which is about 10 times as intense as we have it here. So getting to Mercury is extremely complicated if you want to go into orbit around it, because a simple transfer orbit that slows you down, sends you on an ellipse which touches the orbit of Mercury, you can do that. But when you get there, you'll be traveling far too fast to go into orbit unless you have a disproportionately large amount of fuel on your rocket. So what was done instead was a complicated series of gravitational slingshot maneuvers, flybys of first the Earth, then Venus twice, and then 3 of Mercury, each of which was designed to give up a bit of energy from the spacecraft. So the planet gets a little bit of energy and the spacecraft loses it and gets moved further in, closer to the sun, and eventually slows down enough that it can approach Mercury, do a rocket burn, and actually be captured by Mercury's gravity. You might notice that the timing, the spacing between the successive passes of Mercury gets longer and longer because it's approaching the speed of Mercury more and more closely until it's just about able to make a long burn and get into a highly elliptical orbit, which it then gradually circularized over time. So this complicated maneuver was developed by an Italian aerospace engineer called Giuseppe Colombo, and it's after him that the next probe is named. His nickname is Bepi, and so that's the probe is named after the guy who invented this technique of getting to Mercury. So because Messenger was in orbit, it mapped the entire surface of Mercury over the course of its time there. And this is a sort of standard projection map. And it shows there are no dark areas, particularly, no Maria. There are impact features which have got rays coming out of them. And there are darker regions and smoother areas, but not in the same way that there are on the moon. And that feature there is that bright spot, Nathair Facula. It's actually the brightest point on Mercury, the highest albedo point on Mercury. And Messenger took a close-up of it, which looks like that. Now, this is believed not to be an impact feature, because although there are craters near the middle of it, this white material is a smooth, uniform, gradually decreasing layer as you go outwards. There is no sign of any large, rough ejecta, as there would be around an impact crater. It's just a smooth white material which is draped over the rest of the surface. And it's believed that this is actually some sort of pyroclastic or volcanic material which erupted from somewhere in the center, one of these vents, and spread itself out over the surface of Mercury. It's not it's sort of a volcanic feature rather than an impact feature. There are also these features called lobate scarps, which were seen by both Mariner and Messenger. You can see one of them running across here like this. The colouring, I think, is false colouring, reflecting the height of the feature. The red is high and blue is low. And these scarps are basically overthrust faults, and they indicate that Mercury has been shrinking since it was formed. And so one part of the surface has been pushed up over the other due to the shrinkage. And the number and size of these indicate that Mercury has shrunk by a couple of kilometers since it was formed, probably 3 or 4 billion years ago. So it's not shrinking all that fast, but it's enough to do that to it. And these features cut through the craters and everything else quite well. You can see, I mean, this crater was obviously formed before that scarp, and so was that one. Messenger also found a whole load of these weird-looking hollows in various places. And these are very strange. They are hollows, lower features in the surface with rounded hummocks sort of in the middle, as if something has gradually been evaporating from inside them. And those were very unexpected. But we have seen something similar on the moon. This is a feature called Ina Caldera, which is sometimes called the Blue Lake because it's very blue in color. And these are similar size. This, I think, is about a 5 kilometer square image, and Ina is a couple of kilometers across. And I think you'd agree, they look very similar. They're both slight depressions with these rounded hummocky bits in them. So possibly when we go back to the moon, somebody might visit this and do some geology on it and see if they can work out if these have the same origin. But at the moment, those hollows are something of a mystery. So the next probe will be Bepi Colombo, which is a joint ESA and JAXA mission. At the moment, it's just one spacecraft, which has not yet gone into orbit around Mercury, but when it does, it will split into two. And one of them will orbit the planet predominantly, and the other will be in a wider orbit, which will investigate Mercury's magnetosphere. They were launched in 2018, and again, take about 7 years to reach Mercury in December next year. The mission is nominally a year, but if all goes to plan and it's all working, they're not going to scrap it after a year. They're going to keep it going as long as they can. And this is a picture from one of the Bepi-Colombo flybys. The main science cameras are kind of buried in between the two spacecraft. So all of these images that we've had so far are taken by engineering cameras pointing outwards, which is why you've got bits of spacecraft in the foreground, and the image quality isn't great, but at least it shows that the whole thing is working and gives us another view of Mercury. So based on all of that information, this is our current understanding of what Mercury looks like internally. There is an inner core, which is probably solid, consisting largely of iron, possibly with some mixture of sulfur in there, but it will be solid. However, the temperature of Mercury is such that a pure iron planet would have solidified completely by now. Its temperature isn't high enough for the iron to be pure. And the outer mantle, this outer core rather, is almost certainly a mixture with iron and rather more sulfur, which can remain molten down to about, I think it's nearly 800 degrees. And Mercury's internal temperature is more than that, based on its surface temperature and its infrared emission. And then outside that, there is a rather thin mantle and crust. And so this very large iron core is the reason for the high density of Mercury and its very large mass. It's about 70% of the mass in the core, which is an enormous fraction. And there is speculation that the fact that Mercury has this really large core and not much mantle, and the fact that its orbit is quite eccentric, the solar system, which stripped off a lot of the mantle material, which would have been there according to the way planets are believed to form and the likely concentrations of different materials in the solar nebula. But a big impact which stripped off a lot of the lighter material could very well have changed the eccentricity of the orbit, changed the inclination of the orbit, and left a planet which was disproportionately massive like this. Don't take that as gospel, that's speculation, but it seems plausible to me that that should be the case. Okay, so the last section I want to talk about is what we can do as amateurs to observe Mercury. We're doing for time. Okay. So there are a number of things that we can do, and the simplest one, of course, is just to catch a glimpse of Mercury in the twilight. And I've covered how you do that. The best times are spring evenings and autumn mornings. And obviously you can use a planetarium app like Stellarium for your location to give you a good idea of when is the best time for that. You can just use a telescope and observe things like the phase. That's the next level is observing or imaging the actual surface of Mercury to try and record detail. And that's surprisingly difficult, actually, having spent a lot of time doing it. I can attest to that. And there are a number of, well, one or two special observations that you can make, which I'll come to at the end. The main thing is to think carefully about safety, because, as I said, the best time to observe Mercury, well, as with anything, is when it's high in the sky, because then you are not looking through so much atmosphere and you get the best chance. Of course, that means the sun is out as well, and Mercury is quite close to it. So you have to think carefully about safety, both of yourself and your equipment, if you're doing that. And there is also the challenge of actually finding it in daytime. But both of those things can be done. And there is an observing guide published by the BAA, which I can highly recommend, not least because I wrote it. It goes into a great, probably too much detail in some cases about how to do all of these things. If you're a BAA member, you can download the PDF from the section website. If you would like to buy a paper copy, I do actually have a few here with me. which you can buy from me. I don't get the money, that goes to the BAA. All I get is the fame. It's £10 for a copy of that. And if you really want to down value it, I'll even sign it for you at no extra cost. Not that difficult. The main hazard, of course, in trying to find Mercury and observing it is not Mercury, it's the sun. And in particular, the concentrated heat and light of the sun that would be present in an image. If you can avoid forming an image of the sun at all, then there really isn't any danger. And the best way to do that is to make sure that no light, no sunlight, light baffle over the front of the telescope, or in this case, a solid tube Newtonian. And about half of even the smallest elongation, which goes to 18 degrees. So you can actually make quite safe daytime observations of Mercury over a significant part of its orbit in daytime without putting yourself at any risk. Finding it, though, can be a challenge. And the best way to do that is to start with the sun, which, if you can't find the sun in daytime, then probably astronomy is not the best hobby for you. You need to start with have a solar filter on the telescope, obviously. And the point about starting with the sun, other than having a reference point, is that it lets you focus the telescope. Because you are not trying to find Mercury just in right ascension and declination. You're also trying to find it in focus. If you're looking for a planet or something in the night sky, and you're not quite in focus, when you get there, you will see an out of focus blob. When you're looking for Mercury in a bright blue sky, and it's out of focus, you have virtually no chance of finding it. You need to be in focus. And even then, it's quite difficult. But I hope you can see there is actually a little blob there, which is Mercury at about the 2 o'clock position from that pointer. And the pointer is important because it forces your eye to focus. You can use a crosswire. Some people use a crosswire eyepiece. I happen to have this one, which I made. But if you know that that's in focus in the field of view and you focus the sun with the same eyepiece, then you know when you actually do point at Mercury, you will see something. And because your eye will be focused on the pointer or the crosswire, you will actually be able to focus correctly. You have to close the other eye during the daytime. Otherwise, you'll be looking at the flowers in your garden or a lawn or the cat or something, and that'll just confuse you. You have to close the eye, and then the focus can tend to wander if it's got nothing to latch onto. So giving it something to latch onto is really important. The kind of things you can do are simple drawings of Mercury. This is a very good example by a chap called David Gray, who lives in County Durham. This is a few years ago. I think he's more or less stopped now, which is a shame because he's a very, very good observer. This was done with a 415mm telescope, very high quality telescope, but you can see that his drawing is excellent and it shows similar sort of markings to the SWHAS map. And you can compare those with the maps and see that, yes, she has actually got the same features. This is another set of observations made by an Italian amateur, Mario Frassati, probably in slightly better weather conditions in Italy than we have here. And he actually made his own map of Mercury, which compares very well with the SWHAS map. And this was done with a 20cm Schmidt-Cassegrain. So you don't have to have a 16-inch Dawn Kirkham to do this. You can do this with a reasonably modest amateur telescope, provided you are dedicated and have good clear skies all the time. If you want to go to imaging, then that is also possible, although this is surprisingly complicated too. The main problem with daytime imaging of Mercury is the seeing. And the best elongations to try and image at are ones where it's to the west of the sun, because then Mercury is rising before the sun, reaching a reasonable altitude before the sun gets up and starts cooking everything, and the turbulence kicks in and the seeing degrades. This is a picture by Martin Lewis with his 222mm Dob. And what he's done here is compare the Wynne-Dufoss image for the same time, to which he's added some blur to reduce the resolution to something which is similar to his image. And you can see there's a very good correspondence between those two. Martin is, I should say, an excellent imager of just about everything. And this is one of my own images, again, taken during a fortunate 10-minute slot of really good seeing in August, was it 2020? And again, these images are best taken in the red or the near infrared because the seeing tends to be slightly better in those wavelengths. And also the albedo markings on Mercury's surface tend to be slightly more contrasty. The downside is as you go into the infrared, the resolution of the telescope gets less as well. So there's a compromise to be made. I tend to work in the sort of, this was done with the 610 infrared, so 610 to 710 nanometer waveband. That gives a good balance of seeing and focus and resolution. But again, you can see the image like that and the degraded Wynne-Dupas image show good correspondence. You can pick out quite a lot of features. The smallest features on this are probably half arc second again, so that's typical of what you would expect to get in reasonably good seeing. So I mentioned a special observing project. This is something I've been involved in for the last few years, or been bashing my head against, I should say. And this is Mercury's tail. Now, Mercury's tail was only suggested in about 2001, and it was first imaged in 2008. And it's basically like a comet's tail. Mercury has some light elements on its surface, and it's bombarded by the solar wind and obviously irradiated very fiercely by the sunlight. And those processes generate a very thin, dilute, what's called an exosphere. It's not really an atmosphere of materials around Mercury. And that gets blown back by the solar wind, just like the iron tail of a comet. And this image shows that there. Mercury is hidden behind an occulting disk at this point here. This is a little spot you can see is Mercury. And this is extending for 2,000 Mercury radii. So this is 1 million or more kilometers. It's a long feature. It would extend a degree or two across the sky. But it's very difficult to detect. You have to observe it again during twilight, so it's fairly low down. You need a sodium filter which passes the yellow sodium light that we all love and hate from sodium streetlights. There's another picture of it showing the orange color that you get and the tail stretching away up here. And that little dot is Mercury behind the rather scruffy looking occulting strip. And that's one of my own images from a couple of years ago. Similar kind of thing, partly transmitting occulting strip, because you want to know where Mercury is. And the exposures that are needed for this are tens of seconds. And if you don't block out most of Mercury's light, it will just be a big overexposed blob. You'll still see the tail, but I wanted to see where Mercury was, and in particular, trying to record the positions of any features that might appear in the tail requires me to know where Mercury is going to be. So I have to do that. It makes the whole imaging system a bit more complicated. So there's another complication to this, which is that the tail is not always clearly visible. And that is because when Mercury is at perihelion or at aphelion, it's not moving towards or away from the sun. And so the wavelength band shown by these red lines where the sodium atoms would absorb light is sitting right on the sodium D lines in the sun's spectrum. And so there's very little light there to absorb. And so the sodium in the tail does not get excited and it doesn't glow. So the tail disappears. On the other hand, when Mercury is moving away from the sun, it reaches a maximum radial velocity of about 10 kilometers per second. And at that point, the Doppler shift of the sunlight is enough that the absorption region is in the side of that line, and there's a lot more light to be absorbed. And that is when the tail becomes visible. And this was seen very nicely in messenger data. And these 4 images show Mercury, first of all, here at perihelion. And a little cartoon, and if you can see, there's a red dot which shows where Mercury is in its orbit. Perihelion, you've got the exosphere glowing, but very little in the way of a tail. You get around 90 degrees away from that, you've got a bright exosphere and light coming out from the tail as well, although they've zoomed right in, so you can't really see much of the tail. And you get to aphelion. Mercury's, again, not moving towards away from the sun, so the excitation is very, very little. And because it's further away from the sun, there's less sunlight. This is the inverse square law. There it's close to the sun, there it's 50% further away, so there's less sunlight, and that is reflected in the difference. And then when it's coming back in, you again get a bright exosphere and a bright tail. So you have to have not only Mercury at elongation or close to elongation and high above the horizon, it has to be a few days before or after perihelion or aphelion as well. So it's just one more complication, and you have to have a clear night. So this is my setup to doing this. You don't need a big telescope. This is a 66mm William Optics refractor, to which I have attached a homemade gadget, which has got the occulting strip in here, and then a couple of lenses and the camera I use for imaging. There's also a guide camera, because you need to do auto guiding. Otherwise, you will not be able to keep the image steady. And I put a red dot finder on there just for convenience as well. And all of that sits on an EQ5 mount, which is something I've had for ages and which does have a port for auto guiding. So this can all be carried to my observing site. I can't see this from my garden because I have a very bad horizon. I have to drive up to the top of a hill about 15 minutes away, set everything up there, and then do my imaging. So it all has to be portable as well as everything else. But it does work, and I've managed to get some reasonable results, and the opportunities are few and far between, unfortunately, because the tail is only visible under these fairly limited circumstances for a couple of weeks at most at any one time, and that only a couple of times a year. So you really have to have everything come together very nicely in order to be able to do this. But I've got some decent results. There's another elongation of Mercury coming up in March, which is another favourable one, an evening one. So I shall be out doing this again. So just to summarise all of that, Mercury, as I hope I've explained to you, is a really interesting planet, but it's very difficult to study from Earth because of its small size and its distance and the fact that it's very close to the sun. Almost everything we know about it, we've learned from spacecraft observations, and I'm sure that will only increase during the Bepi-Colombo mission. So the main benefit, I would say, as amateurs, is in improving our skills. In particular, if you succeed in taking an image of Mercury, which shows surface features, the techniques you will have to learn and the skills you will have to develop to do that will benefit your planetary imaging in other ways that you might not have thought possible. But I think, as I said, with the sodium tail stuff, it is possible that we might be able to do a small amount of scientific work which complements at least the spacecraft observations. So with that, I shall say thank you for your attention and take questions.
They're in orbit around the sun as well. So why doesn't it all just travel around as a cloud rather than make a tail?
Because they are, well,
Okay.
why do the particles that are blown off Mercury not just stay in the orbit around the sun rather than get blown back? Well, why doesn't the comet's iron tail stay in orbit with the comet? It's the solar wind that pushes it back.
Oh, okay.
It's very light material. It's not dust grains. It's atoms of those various light elements that are knocked out of the surface by the solar wind protons, excited by sunlight, and so on.
Got another question over here. Thank you.
Cheers. Thank you very much for that talk. Really interesting. Don't hear a lot about Mercury quite often, so really fascinating planet. Thank you for that. I'm actually going to carry on with what Len was talking about with the light elements, which you mentioned towards the end, because I think somewhere that it's very unusual to have light elements so close to the sun, because you'd have thought that they would have been blown away. And I wondered whether you came across any research as to any explanation as to why Mercury might have that, or is it maybe one of those things that maybe Colombo is going to investigate? Thank you.
I mean, just because Mercury is so close to the sun doesn't mean it can't have intermediate weight elements. I mean, astronomers regard hydrogen and helium as gases and everything else as metals. So, I mean, sodium is a medium weight element, if you like. It's not the heaviest by any means, but it's certainly not the lightest. And if in the course of forming the material from which the planets and the solar nebula were made, that sodium or those other elements got incorporated into rocks or boulders or whatever in interstellar space, that would be some chemical combination. So they wouldn't necessarily evaporate and be driven away when the sun ignited and started blowing the solar nebula away. The light elements, like the gases, get driven out to the outer part of the solar system, but the rocky materials, including the elements contained in those minerals, would stay in the center. Hope that answers your question.
Although Mercury has a greater proportion of iron in it than the Earth has, its magnetosphere is only 1% of the value of the Earth. So what are the factors which determine the strength of the magnetic field?
I think it's to do with the convective currents inside the core. That's what most of the Earth magnetic field is driven by a kind of dynamo. And part of that is driven by radioactivity, radioactive decay heating the core of the Earth. And it's the currents that flow in the outer part of the core, because the Earth has a solid inner core as well. It's probable that the Earth's core is has a higher purity of iron than Mercury. Mercury's got a lot of sulfur in it, otherwise it would not be liquid anymore. So maybe there is less, maybe the convection, for some reason, hasn't got started to such an extent. I honestly, I'm not an expert on that.
Okay. Now, with our speaker, Chris, talking about Mercury, it is an interesting planet to see, remarkably difficult, I have to say. I've actually seen it once through my 8.5-inch telescope, and that was a long time ago. That was in 1994. But I've got to say that it made an impression. Okay, so I would recommend anybody have a look for it, try and find it, just for the sheer thing of seeing it, sheer thrill of actually seeing the innermost planets. Well worth doing. And even while Chris was talking, I could actually see the image, and that was a long time ago. So these things, they never disappear. This evening, we've got a full moon, and of course you can see the full moon. Now I'm sure that everybody is in the same boat as me, that we have had constant rain. I have had one clear night in the time since the last meeting, so that's nearly a month. And that was so uncertain that I actually just got a pair of binoculars out and just made sure that all those clusters that I mentioned in the last session were actually still there. So they are. So that it's just rain and cloud that's been obscuring them. So what I'm going to do this evening is we're going to focus on something that we don't normally think about necessarily. We all talk about the constellations like Ursa Major and Ursa Minor. We refer to them a lot, but we don't. There's constellations, we don't tend to think about them very much because they're not really. There's nothing really, I suppose, interesting about them in a sense. I mean, we know the Plough, it's an easy way to find the pole star, and it's the Plough, and that's as far as it goes. But in fact, there are interesting things about that particular constellation, Ursa Major and Ursa Minor. They're binocular and objects you can see through a small telescope. And I also want to refer to another constellation that is connected with the Bears, but in a different way. And that is Boötes. Now, the reason it's that pronounced, you've got that weird pronunciation, is because if you notice, there's an umlaut two dots above the second O, which means that that's why you have to pronounce it that way. It's a bit of a nuisance, really, but that's how it is. So, okay, so we've got Ursa Major up here. I'm just going to see if I can bring it up a little bit larger. There we go. And actually, this particular line drawing doesn't really give much indication of the prominence of the plough, the 7 stars that we call the plough. Now, of course, that's an asterism. I've mentioned this before, that certain parts of some constellations are used for navigational purposes, and of course, the plough is one of them because it points to the pole star. Another one is the sickle of Leo, which is here. There's the sickle of Leo. And the reason that mariners particularly used to use them was if you have a sky that's frustratingly clear, but frustratingly cloudy, but has occasional clear bits, how can you be sure that a star like Regulus, which is used in navigation, you can actually see, is that Regulus or could it be something else? But so you've got an identifier. You have the sickle of Leo, which indicates that you're on the right star. And of course, that is the same with the plough. We refer to the plough, we tend to think of it as the whole constellation. But of course, it isn't. It's part of Ursa Major, which is, of course, the Greater Bear. So there are interesting things about the plough itself, and I'm going to just look at a few for a few minutes, and we'll just have a quick look. Now, the plough is composed of obviously 7 stars. Now, when Charles Mayer gave the stars the Greek designations that we use today, he seemed to somewhat lost his head with Ursa Major, because you get alpha, beta, delta, epsilon, zeta, eta, theta. So you've got this consistent sort of alphabetic numbering sequence. Now, it's rather strange, but at least it seems to work. And the thing is, they are more or less the same magnitude. And in fact, most of them are a similar distance from Earth. The only one that isn't is Alpha. And curiously, that is at 127 light years distant from the Earth, is a fair distance further on than the others, which are about between 81 and 75 light years from Earth. And it also is different in colour. It's actually an orange star, which marks that out as it's just an interesting thing. And it's nice in binoculars if you can sort of scan a constellation and see there's one coloured star. And of course, there's another one. There's another interesting thing about the plough. You have this little star here, and that is Mizar. Its proper name is Mizar. And next to it, if you've got particularly reasonable eyesight, you should be able to see another little star just next to it, a little bit facing backwards, and that's the star Alcor. Now, the two of them have been sighted for thousands of years. In fact, there is a story which I've read, and I can't remember where I read it, that the Romans actually used it as entry into their army by making sure that their people could actually have good eyesight. Whether it sounds a good idea to me to say, well, no, I can only see one star. You'd then get out of being a centurion or whatever, but I don't think it was that simple. I think you probably would still get conscripted. But the thing is, that is an interesting combination of a double star, which actually is part of a system. And a small telescope will show another star between the two of them, and it makes up a nice little sort of pattern in a small telescope. Now, the interesting thing is that both Mizar and Alcor are actually spectroscopic binaries. Now, that spectroscopic binaries, they're binaries that were discovered by noticing the twinning and moving of the Fraunhofer lines going backwards and forwards. And they're of great interest to astronomers these days because, unlike the more distant orbiting binaries, these you can see what happens over a few weeks because they're obviously very, very close. They're close binaries. So they're of extreme interest to professional astronomers and astrophysicists. Thing is, too, that this was discovered spectroscopically by the people of the Harvard College Observatory in Boston, and it was the first real use of spectroscopy for this use. They didn't even know they existed. They just found out that star was double. So there's a bit of history in it as well. Now, one of the things that is on our introductory page of photographs of the various deep sky objects that have been photographed by our members, there's an object there which is the Owl Nebula. That's one of the faintest objects on Messier's list, and it's located about here. It's M97. Let's get rid of that. There we go. So it is, you can see it visually. I have seen it visually, but like a lot of these things, I noticed the last time I saw it was in the 1990s. But it does actually make quite a good photographic or a good image subject there for anyone with a very good setup. And it makes, as we saw, quite a nice little image of a planetary nebula. Also, down here in the constellation that is not part of Ursa Major, it's actually Canis Venatici, which is the two hunting dogs of the bear, which was a constellation invented by the Polish Hevelius, just to use up some stars. And but that is where our famous Whirlpool Nebula is, the Whirlpool Galaxy, the famous M51. So that has also been photographed or imaged using equipment from at our observatory in Flaundon. Now I'm going to try and come out this a little bit and go up. I can go up. Now, another connection with Ursa Major is this constellation here, Boötes. Now, that has the brightest star, Arcturus, which is a really bright star. It's very close. It's about 37 light years distant, so that's why it's so bright. It's actually a nice warming sight on a February night to have a look through at that through a pair of binoculars, because it's got a nice warm glow. It's a yellow sort of orange star type K, and that is and the star is actually moving quite rapidly. Now, it used to be said that it was a star that was actually going through our galaxy from sort of north to south and not sharing the rotation of other stars, which are actually going around like the sun, going around the galactic center. But recent work and an article in Sky and Telescope a couple of years ago showed that this is not actually true, and it is actually following the motion of the other galactic stars. It's just it appears that way, and there were reasons in this article, very good one by Ken Roswell, on why that is and why it appears that way. There are interesting objects in Boötes as well. This star here, which is Epsilon, is a nice double star, but it needs a fairly high power on a telescope. And to be honest, I tend to think of it as really quite it's not as good as it's cracked up to be, as it were. It's supposed to be a nice orangey star with a sort of greeny blue one next to it. They don't look much colour to me. I can't see much colour myself. So I always think that it's depicted rather over the top in pictures. I always say it's a really nice star, really colourful. It's not that good. And the other stars that are of interest are located up here. So these two stars here are actually part of Boötes, because it stretches much further than it shows on this diagram. And there's a couple of double stars up here, Kappa and Omicron, that are the double stars, and they're both in the same field. And it's quite attractive. You get a field, a low power field in your telescope, you'll see, but they're quite nice to have a look at. Also, if you want to try something out as well, if you can see here, you can see there's this line here. This is also part of Canis Venatici, and that is alpha and beta. of that constellation. This one here is called the Cor Caroli, Charles's Heart. It was named that by Edmund Halley, who was actually a bit of what you might call bit of scratching somebody else's back here, because actually his Charles II actually granted him his degree by mandate because he hadn't served enough residency for it to actually be granted by Oxford University. So he had to get a degree from the king. And because of that, he named it Charles's Heart after Charles I. So you can see there's a little bit of nepotism going on here. But that star is a nice, bright, easy to observe coloured double star, rather attractive. You can just about split it in binoculars. But if you use Arcturus and that star there and go halfway between them, you'll come across M3, which is a globular cluster. Very nice one. You can see that in binoculars very easily. It's very easy to find. Even in Watford skies, I know you can see that one. Can give you my assurance that I've seen it, and I've seen it recently. So that's basically what I was going to talk about this evening. So what is just before I finish, what is the connection between Boötes and the bears? Well, you might notice that Arcturus, it's an unusual word, Arcturus. And if you think of the word Arctu, which actually means bear, you get some idea that there's a connection here. And what it is, that the Boötes is the guy that's driving the bears around the pole. Because after all, if he wasn't there to do that, things would really fall apart, because that's what controls the whole sky. So that's what he's doing. He's the bear driver, pushing the constellations round and making sure that after all, everything is in its right place at the right time. So with that, I'll finish now and put my jacket on, I think.